Hello, Matthews, Gatos here. Welcome to section 11.3 Binomial Theorem. In this video, we're going to look at ways to expand binomials such as these using patterns. But before we can come up with the patterns, we need to do these by hand ourselves so we can see what the patterns are. So let's start first of all with x plus y, that's a binomial, two terms, to the exponent of 0. Well, that's just 1 because any base to an exponent of 0 equals 1. X plus y to the exponent of 1. That's just x plus y, because any base to an exponent of 1 just equals itself. X plus y squared. Well, to do this, I want to write it out 2 times and use the distributive property. So you can see I've color coordinated it so you can see how I come up with each part. And then I just have to combine my middle terms here, and I get x squared plus 2xy plus y squared. Let's look at x plus y cubed. That means we multiply it by itself 3 times. But notice we already know what x plus y times x plus y is from the last step. So I only have to multiply it by another x plus y. So you can see color coordinating it there. I expand using the distributive property, and then I just have to group my middle terms, my x squared y's and my xy squareds. So group those all together, and I get that as my final answer. So let's use these 4 examples that we've done to come up with some patterns with variables. When we're writing these, we want to write our terms in alphabetical order. So x and then y, not y and then x. And then write them in descending order of your first variable in alphabetical order. So since x comes first, notice I went from x, 3, 2, 1, and none. So let's look at some of our patterns with our variables. So these are the 4 that we've done. So when we raised it to the exponent of 0, let's start with x. I start with 0. Exponent of 1, I start with 1. Exponent of 2, I start with 2. Exponent of 3, I start with 3. Let's look where we go from there. So this is just 0. Here I go from 0 down to 1. I go down by 1 until I reach 0. Here, 2, 1, 0. So I go down by 1 until I reach 0. Same thing here, down by 1 until I reach 0. So it looks like my first term starts at n, which is the exponent on the outside that I'm expanding, and decreases by 1 until it reaches 0. Let's look at what happens with my second exponent. So y starts at 0. When I raise it to the exponent of 1, it starts at 0. Exponent of 2 starts at 0. So it doesn't matter what my exponent on the outside is, I still start my second term exponent at 0. Let's look at what happens from there. 0, and then I go up to 1. 0, 1, 2. I go up by 1 until I reach my exponent. So see, I stop when I reach a 1, which is my exponent. I stop when I reach 2, which is my original exponent. 0, 1, 2, 3. So I go up by 1 until I reach my exponent on the outside. So my second term exponent starts at 0 and increases by 1 until it reaches n. That's a good start to my pattern. Let's use that pattern to expand x plus y exponent 4. So again, I want my terms in alphabetical order, x and then y. So x and then y. So x starts at my exponent of 4 and it goes down by 1 each time until it reaches 0. Y, the second term, does the opposite. It starts at 0 and it increases by 1 until it reaches the exponent on the outside, which in this case is 4. Now, let's clean that up a little bit. So I don't need y exponent 0. I don't really need the exponent of 1 there. So this is what it looks like. Now, I see some other patterns here. So here are 2 other patterns I see. The sum of both my exponents is always equal to the number on the outside, so 4. So I should always have my exponents add to 4. 4 and 0, 3 and 1, 2 and 2, 1 and 3, 0 and 4. They all add to 4. Another pattern I see is I have an exponent of 4, and I have 1, 2, 3, 4, 5 terms. I will always have n plus 1 number of terms. Now let's look at the pattern with the coefficients, the numbers. So let's look at the numbers. So I start with a 1. The next term, I have a 1 and then a 1. My next one, I have a 1 and then a 1. Here, 1 and then a 1. So it looks like you can see it's branching out here. I'm always going to start with a 1, so let's follow that pattern down. Start with a 1 and over here, end with a 1. Okay, what about the other numbers? So the next time I have another number other than 1 is when I expand it to the exponent of 2. So I have a 2 here, which looks like maybe it might be that, but it's actually not related to that. It's related to the numbers above. So 1 and 1 is 2. I come down here for 3. 1 and 2 is 3. 2 and 1 is 3. So I'm going to follow that pattern here. 1 and 3 is, add those together, 4. 3 and 3, add those together is 6. 3 and 1, add those together, and I'm going to get 4. So let's put that pattern all together. So we know what the pattern is with the variables. Let's just add the numbers in front of that. So 1, 4, 6, 4, 1. And now I've expanded it. Now that pattern that we were just talking about is Pascal's triangle. You always start and end the row with 1, and each term is found by adding the term before. So you see here's row 4 that we just did. 1, 4, 6, 4, 1. So if I were to finish that pattern off, let's do it for row 7. So it's always going to start with a 1, and at the end it will end with a 1. And then to find the other terms, I'm just going to add the terms before. So here, 1 and 6, add those together and I get 7. 6 and 5, add those together is 21. 15 and 20 is 35, another 35. 15 and 6 is 21. 6 and 1 is 7. Notice that in these patterns here, the numbers are actually symmetrical. So here, notice I start and end with a 1. I have a 7 and a 7, 21 and 21, 35 and 35. They will always be symmetrical. So let's put this all together and expand x plus y to the exponent of 6. So since it's exponent 6, I look for row 6 of the Pascal's triangle. There it is. Now for x, remember you start at your exponent, decrease by 1 until you reach 0. And then for y, you do the opposite. You start at 0 and you increase by 1 until you reach your exponent of 6. And so all we have to do now is multiply those together. They're all positive, and then we add. So multiplying all of them together for each one, and then we just add together. Now, sometimes I'm going to ask you to expand something to the exponent of, say, 10. You don't want to sit there and write out 10 rows of Pascal's triangle. So Pascal's triangle can also be written with combinations. Let's look at the pattern. So when I start to the exponent of 0, I'm using combinations. I always start with 0. When I have a 1, it's 1c. When I have 2, it's 2c. When I have 3, 3c, etc. So if I want to write out the row 7 of Pascal's triangle, it's all going to be 7c's. So they're all going to be 7s. So 7c all the way through. Now let's look at the next number. I start at 0, 0 and then 1, 0, 1 and 2, 0, 1, 2, 3. So it looks like the pattern here is the exponent of the second term. I start at 0 and I get bigger until I reach 7. So if I wanted the 7th row of Pascal's triangle, I can list out 7 rows of Pascal's triangle or just use combinations to help me. So let's try that. So 5th row of Pascal's triangle, they're all 5c's, and it's 5c0 all the way up to 5. Now, we can figure this out on the calculator. Remember that little shortcut that I showed you as to how to enter in the combinations easily. So I can see now that the coefficients are going to be 1, 5, 10, 10, 5, 1. Let's put that with the exponents of the first term, which go from 5 down to 0, the exponents of the second term, which go from 0 up to 5. Putting it all together, I get that as my expansion. So you can see this is the binomial theorem with patterns. So to summarize here, your first term, which all we've done is x, but it's not always going to be x, you raise your exponents from the power outside, n, all the way down to 0. The second term, which we've done is y, but it doesn't have to be y, the exponents start at 0 and increase to 1. There's always going to be one more than the exponent number of terms. You can find the coefficients using Pascal's triangle with numbers or with combinations. A good check to see if you're expanding it right is to check that the sum of the exponents equals the variable or the exponent on the outside. So let's try one where we don't have just an x and a y, but it's the same process. So in this one, my first term will be 2. My second term with the sign will be negative 3x. So since I've raised it to the exponent of 4, my coefficients will all be 4c's. 4c's 0 all the way up to 4. I can do that on my calculator, and then I know what each of my coefficients are going to be. So my first term is 2. So I'm going to take 2 and raise it to my exponent, decreasing by 1 each time until I get 0. My second term is negative 3x. Now we want to really pay attention to the signs. So put everything in brackets. Negative 3x to the 0, 1, 2, 3, and 4. Okay, so looking at this, we just have to figure out what each of these are and multiply them. So this is going to be 1 times 2 exponent 4 times negative 3x to the 0. This will be 4 times 2 cubed times negative 3x to the 1. 6 times 2 squared times negative 3x squared. Now negative 3x squared means negative 3x times negative 3x, which is 9x squared. And then do the same thing for this row and that row. So to put it all together, now I just have to do some number crunching. I multiply all those together and I just get 16. I multiply all those together, paying attention to the negative, and I get negative 96x. Multiply these together, it's positive, so I have plus 216x squared. Multiply these together, it will be negative, so subtract. And multiply these together, and it will be positive. Now, it's okay to leave your answer like that, but remember my tip from before, I want to write them in descending powers of x. So this would be the best answer. You can always check your answer on the calculator, which is super convenient. So there it is, my binomial to the exponent of 4. There is what I got as the answer. Remember, the check always happens in the table, so I can see that I've done that correctly. So sometimes we're going to have to use laws of exponents to simplify. So just from 10C, there's our laws of exponents that we might be using in some of these questions, such as this one. So again, this is first term and second term. So first term a squared, second term negative a to the negative 1. So 1 over a, my negative exponent, I can write it as a to the negative 1, which makes it a little easier when I expand. So since I'm raising it to the 3, these will all be 3c's. I can use my calculator to figure out what all of those are. So that's 1, 3, 3, 1. My first term is a squared, so I'll raise that to the 3 all the way down to 0. My second term is negative a to the negative 1, and I'll raise that to the 0 all the way going up by 1. So now it's just a multiplying question. So I have 1 a squared cubed. I multiply those together to get 3, and I multiply those together to get an exponent of 0. Here, multiply the exponents, but it's going to be negative because this is to the exponent of 1. Multiply these together. Now a negative squared will be a positive, but again, multiplying my exponents together. Again, multiplying everything together, multiplying my exponents together. So now I'm going to use the power law, or sorry, the product law to multiply exponents together, which says keep the base the same, add the exponents. So this is just a exponent 6. Multiplying these together, 4 take away 1 is 3 for my exponent. 2 plus negative 2 is 0. 0 plus negative 3 is negative 3. So that's what the first part of my answer is. But When it comes to exponents, you always have to keep it positive. Your final answer can't have a negative exponent. So instead of a to the negative 3, it's 1 over a cubed. So to summarize my lesson here, x plus y to the exponent of n, the first term is raised to the n exponent, decreasing by 1 until 0. My second term in the binomial expansion is raised to the 0, increasing by 1 till I reach an exponent of n. You can always find your coefficients using Pascal's triangle or using the combinations. And remember, there are always n plus 1 terms in the expansion. So now that you've learned the binomial expansion, use my patterns to expand it, not making it bigger and expanding it like this student did. So you guys can move on to your practice questions and textbook questions as needed. I hope this video helped, and I look forward to seeing you for the next one.